Without wasting time, let us straight away jump into the micro revision class. I will try to revise all of the things once again, whatever we have learned so far. So first topic is water supply engineering. In water supply engineering, first topic, population forecasting. Population forecasting methods, four methods important for exam point of view. One is arithmetic increase method. This is a simple formula you have to remember. So past population data will be given. From the data we work out certain information. From there we try to forecast future population. The formula which you have to remember is Pn is equal to P naught plus N into X bar. This formula you have to remember, where P naught is equal to among all population data given to you, the latest known population is taken as P naught. Okay. So N is equal to number of decades or number of years. This N value we calculate, it is Tn minus T naught. It is in terms of years. Then you want to work out in terms of decades, Tn minus T naught by 10. Then you will get in terms of decades. So based on X bar unit, we decide N. So X bar is equal to nothing but average increase in population between successive time periods. So M number of values are there. So how to find out this X value? X value is equal to, it is Pi plus 1 minus Pi. So at different time intervals, population data will be given to you. So using this population data, we try to find out that N value, that X values. So X value X at any point of time is equal to, it is population in the subsequent time interval minus population at present. If we subtract, we will get X at that time. Okay. So X1, X2, X3 are worked out the same fashion. Then we take average of these values. Then by substituting this value X bar, sometimes we work out X bar. So population data is given per year, X bar you will get per year. Population data given once in every decade, then X bar we calculate per decade. So based on that, we substitute in this equation and we work out the Pn value. Pn is future population at any point of time, at the time period. So forecasted population, future forecasted population. Future time Tn. Okay. So at present we are at T naught, then we are working out future time. At present population is P naught, and future population this you have to find out. Understood? So between T naught and Tn, how many number of years are there, or how many number of decades are there? That you have to find out. That we work out by using this equation, and we work out future population. Understood? So in this equation, so there are two variables. One is X bar, the other one is N. To find out this, of course, X bar once you calculate, once you work out, it is constant. For a given X bar, N value at work out, then by using the N value, then you can work out population at any time in future. Okay? This much idea is there, you can easily work out numericals related to arithmetic increase method. Second method is geometric increase method. Geometric increase method, I gave two formulae to you to find out future population at time Tn. So it is P naught into e power R into Tn minus T naught, or otherwise P naught into 1 plus R bar by 100. If R is given, well and good. If not given, we take R bar is equal to, it is R1 plus R2 dot 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 Rm by, sorry, this is not arithmetic average, it is geometric average you have to take. So that's how people go wrong. So R bar is equal to, it is R1 into R2 into dot 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 Rm whole power 1 by m. So R value how to work out? Ri is equal to, it is percentage increase in population. So it is Pi plus 1 minus Pi by Pi. Change in population by original population. At time Ti, population is Pi. At time Ti plus 1, population is Pi plus 1. Between these two periods, Ri is equal to change in population. That you have to work out. Percentage increase in population. Pi plus 1 minus Pi, change in population between these two time periods by original population into 100 will give Ri value. So this is how we work out R bar. So once R bar is known, then formula substitution. R bar to the power whole power n. So when R is given, percentage increase is given, which is assumed to be constant, we use this expression. If R is not given, then past population data is given, then we generate R bar value. R bar value, Rn, both of them are one and same only. So n value same as it is. N is equal to Tn minus T naught in terms of years. In terms of decades, you work out En minus T naught by 10 decades. Okay? This is how we work out future population by geometric increase method. So in this question, R could be unknown. In this question, Pn could be unknown. In this question, Tn could be unknown sometimes. Anything could be unknown. One equation, one unknown, anything they may ask. Generally, future population they will ask. Understood now? Third method is incremental increase method. So again equation is equal to Pn is equal to P naught plus n into x bar, like arithmetic increase. The extra thing added to this is n into n plus 1 by 2 into plus or minus y bar. The extra thing that we need to work out in this case is y bar. This y bar is equal to, it is y1 plus y2 dot 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 ym by m. Okay? So where how to find out y bar, yi value? Yi values to work out, you have to compare xi values. So xi plus 1 minus xi you take, you will get yi values. So that's how we can find out yi values. Then we work out y bar. Then x bar we know how to work out. So xi values how to find out? It is pi plus 1 minus pi. That is xi. Like x1, x2, x3 will work out. Then based on that x bar we can find out. Then x bar is equal to x1 plus x2 dot 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 xm by m. So x bar also required and y bar also required. Both we work out. Sometimes y bar may be negative also because it is increment. So all in future only increment over increase is there, you will get positive y bar. Sometimes decrement also may happen. In that case automatically y bar become negative. So y bar may be sometimes positive, sometimes negative, no matter. Method will take care of that. So you have to simply remember that equation. Pn is equal to P naught into n times x bar plus n into n plus 1 by 2 into plus or minus y bar. Sometimes it is positive, sometimes it is negative also. Understood? That is incremental increase method. The next method is decreasing growth rate method.
Or decreasing rate of growth method. Anyway, you can answer.
Here also you have to remember only formula. So Pn is equal to P naught into 1 plus R naught minus D bar by 100. The extra thing is R naught. 1 plus and D bar. R naught minus 2D bar by 100. We keep on write like this till up to nth decade. In D bar by 100. Okay? This is the equation which you are supposed to remember. So this D bar is equal to, we work out by using D values, D1 plus D2 dot 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 dm by m. So D at any point of time is equal to, ith time period is equal to, you have to compare R values, Ri minus Ri plus 1. Percentage increases you calculate, then you can calculate D value. D bar is nothing but average decrease in percentage increases. Understood? So R naught is among all percentage increases, latest percentage increase is taken as R naught. latest known percentage increase. Percentage increase in population. That is taken as R0. So generally, two methods are very important. One is geometric increase method, other one is incremental increase method. First method, nothing is there, simple, that is. Last method also little lengthy method, so little lengthy equation you have to remember, therefore very rare they ask questions. So second and third are very popular. Okay, this is the one regarding population forecasting. One more method is a logistic curve method, that is not required. Okay, this is coupled to water demands also. Population forecasting is coupled to water demands. So average daily water demand is equal to average daily water requirements of city or water demands of a city.
This is
Q, which is equal to population into per capita water demand.
Okay. This is always
constant. What is constant? Per capita water demand only one time we estimate. So once you estimate, forever it remains constant. So what will change from time to time? Population changes from time to time. So population is a variable. Per capita water demand, once you estimate, it always remains constant. Okay? Population keep on changing. Therefore, Q is straight away proportional to population. Population increases, right? Q also increases. Population decreases, Q also. Population never ever decreases, always increases. Therefore, water requirements keep on increases time to time. Though what per capita water demand remains same, but water requirements increases because of increase in population. Okay. Next thing is, so to work out this per capita water demand, we force you to consider water demands, all types of water demands. So per capita water demand is expressed in LPCD. LPCD stands for liters per capita per day, liters per capita per person, something like that. So water demand in LPCD is equal to, per capita water demand in LPCD is equal to, so to work out per capita water demand, following demands of a community are considered. To find per capita water demand, all types of water demands of a community are considered. Understood now? All kinds of demands we have to take into account. That is domestic water demand. Normally domestic water demand is 135 to 200 LPCD as per IS code. Industrial water demand, as per IS code minimum, we need to provide 50 LPCD. Institutional commercial water demand, for this we need to provide minimum 20 LPCD. Fourth, demand for public use, public utility. This and all we discussed in detail, theory related to them. 10 LPCD. So all these things put together is total per capita water demand of a community. Then 5 demand. Fifth one is 5 demand. So using empirical formula we work out 5 demand. Estimated by empirical formula. Then demand to compensate loss in theft. This is taken anywhere between 5 LPCD. Therefore, total per capita water demand of entire community normally range anywhere between 270 to 335 LPCD. This much water is provided more than sufficient. Total per capita water demand for entire community, entire population living in a community. Per person 273. So this 273.35 account all demands. Fire demand to compensate loss and theft, industrial demand, including domestic demand. Okay? This is the thing. Design period not that important. Anyway, coming to sources of water, not so great topic, that is for GATE point of view. Just have idea. So we have got two types of sources. One is surface sources. Second one is subsurface sources. What you need to know is quality wise which is good, quantity wise which is good. Quality and quantity comparisons have to make. Surface sources example is rivers, lakes, reservoirs, etc. Subsurface sources are right springs, then infiltration works, infiltration gallery or infiltration well, then normal wells. Okay, whatever it may be. Quality wise, surface water, subsurface water is good. Quantity wise, they are poor. Quantity wise, surface water is good. Quality wise, they are poor compared to groundwater, subsurface water. So, surface water, quantity is more, but quality is poor. Surface water naturally subjected to some purification while passing through ground. Okay. Subsurface water, quantity is less, quality is superior. Quantity is less available, but quality is very high. Okay, which is best, which is bad. That much idea is more than sufficient. Then collection of water. Collection of water is made by intakes. Water from surface sources collected from intakes. Collected from intake. So intakes are the means of collecting water from surface water bodies. Without intake, it is not possible. So intake is a structure constructed at surface water bodies for the safe withdrawal of water. For the safe withdrawal of water. Irrespective of the availability of water resource, we need to collect constant amount of water. That is possible only with the help of intakes. That's it. Okay. So we have got river intakes. Intake constructed river is called river intake. We have got reservoir intake. Intake constructed reservoir is called reservoir intake. Lake intake, canal intake, etc. Okay. That's about intake. Conveyance of water. Conveyance means transport. So water conveyed by two methods. Water conveyed from source to a community by one gravity conveyance by gravity method or by pumping method. Gravity conveyance. Pressure conveyance. So normally gravity conveyance uses gravity conduits. Gravity conduits. So example is canals. Canals are open channels. Okay. Pressure conveyance. The closed conduit conveyance. Example, it requires pipes and pumps. So pressure conveyance more we recommend compared to gravity conveyance. Pressure conveyance is preferred to gravity conveyance in case of water supply. Therefore, if at all they ask any question, there is pressure from pressure conveyance. So pressure conveyance required pump and pipe. So design of pressure conveyance is based on mechanics it is. Design is based on 1. Flow continuity equation, 2 is coupled with the Darcy-Weisbach equation or Manning's formula. where area is equal to wetted area is pi by 4 is square. Okay. This you can write it as Q by area V.
Is equal to
Using these three equations you can find out two things. One is diameter of the conveying vane, another one is head loss. Once the diameter is known, then head loss, finding head loss, no difficulty at all. Okay.
pressure conveyance open channel, that is designed. That is
Special topic, open channel flow topic is there. There they teach you. Here we rarely use pressure gravity conveyance for carrying water. The very important topic is quality of water or water quality. We test water quality before water is supplied to public. Because public use this water. Many of the people they depend on municipal water connection. Public are living upon our Medsi, isn't it? Engineers Medsi. But engineer has to be careful while serving the public. If water matches all water quality standards set by Government of India, then only supply is made. So water quality. So raw water is very bad in quality. We convert raw water into filtered water by applying water treatment. Raw water means full of impurities. Water with full of impurities converted into wholesome water. Raw water is converted into wholesome water. Wholesome water is treated water after treatment. So in between what is there? Treatment is there. Raw water if you treat, then you can convert into raw water into wholesome water. Understood? So there is a water treatment in between. We test water quality is nothing but testing of water.
We come across with water testing two
places. Raw water applied to treatment.
Water treatment plant is located at one side.
Wastewater dealing plant is located at different side. Water treatment plant this is.
applying treatment, raw water convert into wholesome
some water. So two places we come across with treating water. One is raw water quality we test. Again we test treated water quality also. Raw water is full of impurities. For applying into before applying application we measure raw water quality. Here we conduct testing. Again treated water also we test. What purpose? How much biodegradable matter still present. Sorry. So two times we test water. Once before treatment, once after treatment. How much wholesomeness water has attained? Wholesome water is that water which is not 100% pure. At the same time, doesn't contain anything harmful to human health. So that level you treat, we are protected. Not 100% pure, but do not contain particles larger than 50 micron. Sorry. Do not contain particles which are harmful to human health. Could be any particle. Harmful to human health. They are called wholesome water. Raw water is full of impurities. Water with the full impurities. Full of impurities is known as raw water. Some North Indian faculty and students, they know it as a raw water engineering. Raw water engineering. That's not correct word to be used. It's a water supply engineering, not raw water engineering. Water supply system deal with raw water. So some people in North India, North Indian teachers, so they call it as raw water engineering. Anyway, whichever name you give, no matter, what is important is subject understanding is important. Okay? Here we test three water qualities. Three water qualities are tested. One is physical water quality. Two is chemical water quality. Three is biological water quality. Okay? Three water qualities we test. Physical water quality, chemical water quality and biological water qualities we test. So physical water quality, 4 parameters we test. Physical water testing. It is called one is temperature, second is color, third is turbidity, Fourth is odor and taste. These 4 parameters we test, and they should match water quality standards. Then only it is known as wholesome water. So temperature tested by thermometer, tested by device known as thermometer.
And drinking water
Standard. What this is? Temperature in drinking water, right? Anywhere between 10 degrees Celsius to 20 degrees Celsius. The drinking water standard. As per Indian government, we follow IS 10900.
Drinking water standards
are taken from IS 10500. Okay. Temperature should not be less than 10 degrees. Temperature should not be more than 20 degrees. More than 20 degrees promote growth of microorganisms. Less than 10 degrees, it doesn't flow properly in a system. Color. Measured by what? Tintometer. Measured by tintometer. And expressed in terms of color units, and standard is 5 to 20 color units or true color units. TCU. Unit of color is TCU. Okay. Third one is turbidity, measured by turbidimeter.
turbidity is
Expressed in terms of TU or JTU. Turbidity units or JTU, Jackson turbidity units. Generally, turbidimeter, this is known as nephelometer. When you use nephelometer, nephelometric units we express in terms of NTU. That's why general turbidity units. TU stands for, it could be JTU or it could be NTU. So turbidimeter is a digital electronic device, quickly measure turbidity. Okay? Therefore it is very popular. Turbidimeter known as nephelometer. Turbidity measured by nephelometer. Exactly you want to measure nephelometer you have to use. Okay. Then fourth parameter is odor and taste. Odor measured by osmoscope, device known as osmoscope, and threshold odor number should be less than or equal to 3. Drinking water standard, it should meet more than 3, It is objectionable. Threshold odor number is equal to A plus B by A. So one numerical is possible to work out threshold odor number. Okay, A is equal to volume of distilled water in ml B is equal to volume of diluted water. This is volume of water sample. A. This is volume of distilled water. B is volume of distilled water. Volume of water sample in ml. Volume of distilled water used for dilution. So A plus B is nothing but capacity of osmoscope. Capacity of osmoscope. Okay, which is normally 300 ml. It can accommodate, sorry, 200 ml. BOD bottle 300 ml, osmoscope only 200 ml. I am purposefully writing wrong information so that you can correct me. Because already you have studied this. Okay? This much idea is more than sufficient. And coming to chemical water quality, drinking water standards you have to remember. So two places there is a scope to ask questions. One is pH. pH is equal to log 10 1 by H plus ions. pH plus POH is equal to 14 and H plus into OH minus ions is equal to H plus into OH minus ions product is always constant, which is equal to 10 power minus 14 moles per liter. From this he is asking numericals in exam, GATE exam. First parameter. Second parameter is total alkalinity. This total alkalinity we work out by formula OH minus into 50 by 17 carbonates into 50 by 30 bicarbonates into 50 by 61. Assuming that their concentrations are given in milligram per liter. Then straight away you can calculate total alkalinity in nutrient system milligram per liter as CaCO3. You get it total alkalinity in milligram per liter as CaCO3. Total alkalinity in milligram per liter as CaCO3 you can also work out by using equivalent weights, that is unit system H plus OH minus ions, carbonate ions, they are expressed in milliequivalents per liter. Then just multiply with 50. Carbonates into 50 plus bicarbonates into 50. See, any one of them was missing in the question means you can take it as 0 comfortably. It is not there, they need not give. Present, they will give. If they are given in milliequivalents per liter, equation you can follow is this one. Okay? Milliequivalents per liter. So, we discussed about conversions milligram per liter to moles per liter, moles per liter to milligram per liter. How to convert? Concentration of X in milligram per liter is equal to X could be anything. Concentration of X given in moles per liter into, right, molecular weight of X into 1000. So molecular weight has got units gram per mole. So moles cancel. We left with grams, gram per liter. To convert grams into milligrams, we use this expression. Into 1000. Multiply 1000, grams convert into milligrams. Understood? Vice versa. Concentration of X in moles per liter you require. It is given in milliequivalents per liter. Then what to do? Concentration of X in moles per liter is equal to concentration of X given in milligram per liter. Exactly opposite. Molecular weight of X into 1000. So by like this we can carry out conversions. Okay. Next is total alkalinity. So alkalinity you can also work out by titrometry. So two alkalinities we work out. One is P alkalinity and T alkalinity. Knowing this P alkalinity or T alkalinity or M alkalinity, methyl orange alkalinity, right? So we call it M alkalinity. You can find out substances that cause alkalinity in water. So this we take it as P, this we take it as T, T or M, whatever it may be. So concentration of substances that cause alkalinity in water we can work out by using this P and T relation. Relation between P and T. Then substances that cause hardness. Hardness causing substances. Oh, sorry. Using this P and T values we find out substances that cause alkalinity to water. OH minus, carbonates, and bicarbonates. Dots I am keeping on the top, they represent charge. OH minus, that means it has got minus 1 charge. CO3 double minus, that means it has got 2 minus charge. 2 minus also you can write. HCO3 minus means it carry only 1 charge. Valency. Okay? So P is less than half T, P is equal to half T, P greater than half T, and P is equal to T. Okay? So this table if you go remember, then you can work out. 0, 0, T, this is last column is T0, 0, middle column is 0, T0. Since T is equal to 2 times P, P is equal to half T, you can also write 2P. Then at the top of the middle column also 0, 2P, and last line, you have to only last column you have to fill up. So when you sum horizontally, it should be T, it should not be more than T. So to get this value T, so I need to add 1 T and it subtract 2P, 2T minus 2P. Then this is also 0, these two columns you have to fill. Bring this and reverse it. This is 2P minus T. Then to get a T value, I subtract minus 2P here, minus 2P minus plus 2P cancel out, 2T minus T, T. So if you horizontally sum up, it is T only, can't be more than T. Understood? This table you have to remember to work it out. Right. That's alkalinity. Next, hardness. This is also very important parameter. Frequently they are asking questions. Hardness in water is caused by, mostly caused by divalent, metallic, cationic substances. Mostly. So total hardness is equal to normally expressed in milligram per liter as CaCO3. We denoted by TH, total hardness. Hardness is caused by two types of substances, calcium and magnesium. So calcium concentration Ca2 plus into 50 by 20, magnesium 2 plus into 50 by 20. 50 by 12.2. 12. Magnesium molecular weight, how much it is? Molecular weight is 24.0, actually 0 point something, but valence is 2, therefore 24 by 2, 12 it is. Okay? Provided that concentration of calcium and magnesium are given in milligram per liter. Concentration is given milli equivalents per liter. Total hardness is equal to calcium into 50 plus magnesium into 50. So also milligram per liter as CaCO3 you will get milligram per liter, you will get milligram per liter. Okay? That's how we work out hardness in water. This is also in milligram per liter as CaCO3. This is given in milli equivalents per liter. Milli equivalents per liter. So I gave you how to convert moles per liter to milligram per liter. Let us work out how to convert equivalents per liter to milligram per liter. Milligram per liter to equivalents per liter. Concentration of any substance in milligram per liter is equal to concentration of the substance X given in equivalents per liter. This you have to multiply with the molecular weight of X. This is gram per equivalents. Sorry, equivalent weight of X. Equivalent weight is different, molecular weight is different. Gram per equivalents into 1000. Equivalents grow, gram per liter, grams to convert into milligrams. Is expressed here. Milligram per liter as CaCO3, you have to express. Therefore, you should be careful. It is gram per equivalents. So equivalents get cancelled. Gram per liter converted into milligram per liter as CaCO3. milligram per liter as CaCO3. This is how we can work out. Similarly, milli equivalence is given. General I'm writing.
That's all.
So, similarly, their concentrations are expressed in equivalence per liter. Concentration of X given in milligram per liter. Equivalent weight of X. Equivalent weight of X has got units.
Into 1000
gram per equivalence, that is. It is given milli equivalents per liter.
When you have been asked to express in milli equivalence per liter,
Concentration of X given in milligram per liter by equivalent weight of X. That's all. If you are thorough with this, your journey will be smooth.
Okay?
So, we can work out easily these things. We can also find out total hardness by working out carbonaceous hardness and non-carbonaceous hardness. Carbonaceous hardness, in our language we call it as temporary hardness. Non-carbonaceous hardness we call it as permanent hardness.
Okay?
So total hardness is equal to sum of temporary hardness and permanent hardness. Technically it is known as carbonaceous hardness and non-carbonaceous hardness. CH stands for carbonaceous hardness.
This
Stands for permanent hardness. Which is also known as non-carbonaceous hardness. CH means carbonaceous hardness, NCH means permanent hardness or non-carbonaceous hardness. Understood now?
Okay? So these are the place where you can work
Expected some numericals and estimation of CH and NCH also important. How you can find out? So to find out CH and NCH, the base is total hardness and total alkalinity. Based on total hardness and total alkalinity. Carbonaceous hardness is equal to, it is minimum value of total hardness and total alkalinity. Non-carbonaceous hardness is equal to, this is total hardness minus carbonaceous hardness. That's how we can work out. Okay. Based on this, there are keep on asking numericals in exam. GATE exam, ESE exam, numericals are keep on asking. Find carbonaceous hardness, non-carbonaceous hardness, or total hardness, right? Calcium, magnesium will give you total hardness they ask. Okay. In addition to this, the other water quality parameters, chemical water quality parameters which you have to remember is DO. DO means dissolved oxygen measured by Winkler's method. And drinking water standard. In drinking water DO should be anywhere between, right? Should not be too high, should not be too low. So 3 to 4 milligram per liter should be there. Hardness also, drinking water standard is there. So drinking water standard with respect to hardness is total hardness preferably should be less than or equal to 300 milligram per liter as CaCO3. Similarly, total alkalinity, drinking water standard. pH 6.58, total alkalinity should be preferably less than or equal to 200 milligram per liter as CaCO3, and total hardness should be preferably less than 300, not equal also not allowed. These three parameters I give drinking water standards. Similarly, next parameter is DO. DO stands for dissolved oxygen. So dissolved oxygen in water is measured by Winkler's method. DO standard in drinking water is 3 to 4 milligram per liter. Should not be too low, should not be too high. Too low means water become unpalatable. So too high means water cause corrosion. DO less than 3, water become unpalatable. Water smell bad, water taste bad. Smell bad and taste bad. DO greater than 6 very high amounts present, normally 6, 8, something like that. I can't give any value, should not be less than 3 at any cost. So high DO in water also cause corrosion. I don't know the exact figure. High DO in water also not recommended. So better to maintain anywhere between 3 to 4 is always good. At any cost it should not be less than 3. Above 3 okay, but too high amounts cause corrosion problem. Next parameter, fluorides. Fluorides also typical water quality parameter. Fluorides less than 1 milligram per liter cause dental caries problem, dental cavities.
It's called
Teeth staining cavities and teeth staining problem. Okay. Fluorides more than 1.5 milligram per liter. It is called mottling of teeth. Mottling of teeth means teeth staining. Yellow patches will form to the teeth. It is also called teeth staining. Teeth stains. Stains means colors. So yellow disfigurement you can notice. And excessively high concentration cause fluorosis. This is known as fluorosis. So again, fluorosis two types, dental fluorosis and skeletal fluorosis. Both are very dangerous. Fluorosis normally occur when fluoride's concentration is greater than 1.5 milligram per liter. Two types of fluorosis we suffer. One is dental fluorosis, second one is skeletal fluorosis. Skeletal fluorosis. Okay, bone fluorosis is also called. So bones become weak. Teeth fluorosis. Anyway, either of them are not recommended. Therefore, drinking water standard, fluorides in drinking water should be anywhere between 1 to 1.5 milligram per liter. Should not be less than 1, should not be more than 1.5. Understood? Fluorides in drinking water should not be less than 1 milligram per liter. Should not be greater than 1.5 milligram per liter. So we should maintain anywhere between 1 to 1.5 milligram per liter. Okay, I am writing because already we discussed, already we solved problems. Numericals and all we worked out using these expressions and all. So that's why I am not again giving details regarding them. Is it okay for you? Twenty-four slide, you want? Okay. Anything you want to ask me? Next is nitrates. Nitrates concentration in drinking water should be less than 45 milligram per liter. More than 45 milligram per liter present, it causes a disease known as methemoglobinemia. If nitrates concentration is greater than 45 milligram per liter, it causes blue baby disease. Blue baby disease is caused by nitrates, or technically, medically it is known as methemoglobinemia. Okay? So nitrates in drinking water we measure by calorimetry, and it should be preferably less than 45 milligram per liter. So fluorides, nitrates. Then what else important thing? In chemical water quality, iron and manganese, if present in excess concentration, cause color to water. If present in excess cause color to water. So therefore they should be within the limits. One more point there, total hardness, total alkalinity. Hard water is good for health actually, but hard water is good for health doesn't mean that we can supply hard water, but bad for property. So hard water cause corrosion. Okay, corrosion problem is there with hard water. Alkalinity also not so problem, but alkalinity cause scaling problem, bitter taste it also impart bitter taste. So hardness cause corrosion, hardness cause scaling, so many problems are there. Therefore we don't recommend hard water. Drinking point of view it is okay, good it is. That's it, chemical water quality. Next coming to biological water quality. Only one thing you have to remember, that is MPN, most probable number. Most probable number we pick up from tables. MPN, most probable number, read from table from the given E. coli test results. From the given E. coli test results, you work out MPN value. So MPN value we measure from the tables, MPN tables. Read from MPN tables from the given E. coli test results. How to rate and all we already discussed. So drinking water standard with respect to MPN is MPN should be preferably less than or equal to 1 number per 100 ml. So more than 1 number are there, it is objectionable. Up to 1 number okay, because 50-50 probability it is, because we apply probability concept. Clear now? So next topic is sedimentation. In sedimentation topic, so many formula are there. First, we work out settling velocity of the particles. So settling velocity of any particle we can work out by using Stokes law. The Stokes law is Vs square is equal to 4 by 3 into G rho P minus rho W into D by CD rho W. This is called Stokes law, Stokes equation. But if you simplify this equation for laminar flow condition, then the Stokes equation we can reduce into very simple formula. Vs is equal to G into rho P minus rho W into D square by 18 nu. Or in terms of kinematic viscosity, we can also write in this form 18 nu. Okay? For laminar flow condition. That's the first thing. Second thing is surface loading rate or surface overflow rate, for which sedimentation tank is designed, work out by using Q by surface area. Right? Surface loading rate or surface overflow rate V0 is equal to Q by surface area. This is surface area of sedimentation tank. So for rectangular sedimentation tanks, surface area is equal to L into B. For circular sedimentation tank, surface area is equal to this pi by 4 D square. This is one parameter, design parameter, very important design parameter. Surface loading rate or surface overflow rate. Okay? And second design parameter is detention time. Detention time is equal to volume by flow rate. volume of sedimentation tank by flow rate. That will give detention time. Where volume is equal to L into B into H for rectangular tanks. Volume is equal to pi by 4 d square into H for circular tanks. Okay? So you can fix up the dimensions with the help of them. In addition to that, the extra things that you need to remember in case of the sedimentation tank design is flow velocity. Horizontal flow velocity is equal to Q by cross section area. So Q by B into H. That is also important. For rectangular tanks especially. Okay. Rectangular tanks are only important for us. Then in addition to that, what extra you need to remember is wear loading rate. Q by length of wear. WLR represent wear loading rate. Wear loading rate is equal to Q by length of wear. All this formula, based on this formula, we worked out numericals already. Okay. In addition to that, we wrote two conditions. Particle removal efficiency. Particle removal efficiency. Particle removal efficiency. Efficiency of ith particle removed from flow. Efficiency of ith particle removed is equal to settling velocity of ith particle by V naught into 100. Okay. Overall efficiency. Overall particle removal efficiency. Overall efficiency. Efficiency overall means so many particles are present, therefore percentage of each particle present and their respective efficiencies by 100. It will go overall. You can also work out this particle removal efficiency in terms of concentration also. Concentrations are given also, you can work out. Getting it or not? So concentrations, if you know, so efficiency also equal to concentration of ith particle removed is equal to C in minus C out of ith particle in water by C in of ith particle into 100. This which we can also equate to settling velocity of ith particle by V naught into 100. Similarly, overall removal efficiency overall is equal to sigma Pi in terms of concentration also you can write sigma of all particles, C in minus C out of all particles if you take, and sigma C in of all particles, okay, sigma if you put all particles it will come into 100. This way you can work out. So which is also equal to, which you can also equate it to sigma Pi into efficiency of ith particle by 100. Then in addition to that, conditions for 100% removal also we saw. What are the conditions for 100% removal? Settling velocity of the particle should be more than surface loading rate. Then only 100% removal happens. So for 100% removal of particles, first condition is settling velocity of the particle should be greater than V naught. Second condition is settling time of particle should be less than or equal to detention time of water. So these two conditions also very important. One is settling velocity of any particle should be greater than or equal to V naught. Second is settling time of any particle should be less than or equal to detention time of water. So any of these two conditions satisfied, particles are removed 100%. This is also very useful expression in sedimentation tank design. Okay? This many equations, if you remember, more than sufficient for you to work out any numerical in GATE exam. So sedimentation tanks, any problem you can work out with the help of them. Okay? Then coming to Sedimentation aided with coagulation, or simply people write it as coagulation topic. Sedimentation aided with the coagulation. So in this topic, first numerical concept is right. Then finding what is that chemical requirement for alum dose. So for a given alum dose, alkalinity required is equal to it is 3 into 100 by 666 into alum dose. This is the first formula related to that. So he is asking questions based on this formula. Then if there is alkalinity deficiency in water, we work out. So alkalinity deficiency is equal to, in water, it is alkalinity required minus alkalinity present. So alkalinity present is more than alkalinity required, no deficiency. Alkalinity already present in water. Otherwise deficiency. To fulfill the deficiency we add lime. So therefore dose of lime required or quick lime required as CaO is equal to it is 56 by 100 into alkalinity deficiency. Straight will get this in milligram per liter. Here also will get milligram per liter as CaCO3. Alkalinity expressed in CaCO3 terms, in terms of CaCO3. This is one question. Ferrous sulfate if they use. So what is the quick lime required for ferrous sulfate? So dose of quick lime required for ferrous sulfate. In case of ferrous sulfate is used as a coagulant. Then it is 56 by 278 into 1 part of ferrous sulfate require 278 parts of ferrous sulfate require 56 parts of CaO. 1 part require how many parts? Like that we work out. 56 by 278 into dose of ferrous sulfate. So these are various kinds of numericals we worked out. In addition to that, what they ask, total alkalinity required, total lime required, total alum required, something like that. So total alum required means what you need to use, total alum required per day. What you need to do? Q into alum dose. So substitute Q in MLD, alum dose in milligram per liter. You will get a alum required per day. So once you get per day, then you can work out per month, you can work out per year, anything. So you will get straight away in kilogram per day. Similarly, total ferrous sulfate required per day. Same, instead of alum dose, ferrous sulfate. Ferrous sulfate required per day is equal to Q into dose of ferrous sulfate. Same, this is substitute in MLD, this in milligram per liter. Then you get this answer in kilogram per day. Similarly, total quick lime required per day as CaO required is equal to, how to find out? Q into dose of quick lime. Multiply this MLD, this in milligram per liter. You get so and so kilogram per day. Okay? Per day you work out, per month you can find out, per year you can find out. So you may ask per month, per year, something like that. So if all these equations you are thorough, then you can comfortably work out numericals in chemical requirements in coagulation. Okay? In addition to that, This coagulant dose is fixed by jar test. Fixed by conducting jar test. Okay, that much idea is there, more than sufficient. So class is scheduled up to what time? This session is scheduled up to what time?
To what time it is
Scheduled?
Up to what
Time it is scheduled, I am asking. 2:30, yeah? This slot is scheduled for how much time? 1 o'clock we started. 1 to 3 or 1 to 2:30? Okay. We'll have class up to 1 to 3. Then next session we'll have 4 to 6. Okay. We'll finish up. Next. Design of flocculator is another numerical question from coagulation. In flocculator design, 3 things we design. One is rapid mixing unit. Design of clary flocculator. Clary flocculator consists of 3 units. One is rapid mixing unit, right? Second is flocculator. Third is sedimentation tank. All these 3 things put together, it is called clary flocculator. So rapid mixing tank is designed based on and flocculator. Both of them are designed based on 2 things. One is detention time, second one is velocity gradient. So using detention time, what you can find out? Volume. Detention time is equal to, detention time will be given to you for rapid mixing unit. Detention time is you provide detention time is equal to 1 to 3 minutes and velocity gradient G is equal to 700 to 1000 second inverse. So using detention time, what you can find out? Okay, volume of the rapid mixing unit, Q into detention time. This volume is equal to, it is square type tank, B into H, because rapid mixing tank is square type or circular type. For square type tank, for circular tanks, it is pi by 4 d square into h. For circular basin, this is diameter. Okay, this square type tank, this is circular. That's all. Generally we provide h value 1 meter to 1.5 meter. So volume is known, volume by, okay, then we will get B and H. Surface area you can find out. So surface area, this is equal to, this volume by depth. So B into B is the surface area for square type tank. So from this we can find out B value. For circular tank it is diameter, we can work out. Okay. Surface area for square tank is B into B. Similarly, velocity gradient, if you cross check and verify how much you are supposed to get, then design is okay. Verify with velocity gradient, G should be, G is equal to root P by V mu. and you should get anywhere between 700 to 1000 second inverse, then design is okay. Where V is equal to power imparted to water in watts, V is equal to volume of the rapid mixing unit, mu is equal to dynamic viscosity of water. So we have used this formula and worked out some numericals also. Okay? G value is supposed to get anywhere between 700 to 1000 second inverse. Similarly, flocculated design, we provide detention time 20 minutes to 40 minutes, and velocity gradient we provide 20 to 80 second inverse. So detention time, using detention time, what you can find out? Volume Q into detention time. It is a rectangular tank. Okay, so volume is equal to L into B into H. So H value normally we provide anywhere between 1.5 meters to 3.5 meters. Then you can find out surface area of this tank, which is equal to L into B. Using L is to B ratio, we will find out length of the tank and width of the tank. That's all. Design of flocculator. So once you design the flocculator, next we can verify with the G value. So when you verify with G value, G is equal to P by V mu, we are supposed to get G value anywhere between 2 to 80 second inverse. Because it is a slow mixing unit, so slowly it rotates, therefore G value is very, very low. Velocity gradient is low. Then only design is okay, otherwise it is not okay. Then design is okay. And sedimentation tank designed here is based on surface loading rate only. One is surface loading rate or surface overflow rate V0, that we provide anywhere between 20 to 30 meter cube per. Of course, we will give you, no need to worry. And second one is detention time. Generally detention time we maintain 2 to 4 hours. Okay. So using surface loading rate we can find out surface area Q by V0. Using detention time we can find out volume. Then rest of the dimensions you can find out. L into B, surface area is equal to, using L is to B ratio, you can find out length of the tank and width of the tank. Okay. This is how we can design sedimentation tank as well for a clary flocculator. So that's about coagulation. Coming to filtration. So for slow sand filters, just fixing the dimensions, slow sand filter design. Any filter is designed based on rate of filtration. So first what we do, total surface area of filter we work out. Slow sand filter required. So Q by rate of filtration. Normally rate of filtration will be given for slow sand filter anywhere between 100 to 200 liters per hour per meter square. This will be given to you. Okay. So once you get this, there are two ways we approach the problem. One is after finding total area, fix number of filters N, find size of each filter. What is the size of each filter? L and B. So how to find number of filters? N is equal to, if N is fixed, how to find size of each filter? You get area of each filter, that is L into B, which is equal to total surface area by number of filters in operation. So using L is to B ratio, you can find out length of the filter and width of the filter. And method 2 is fix size of each filter L and B, find number of filters. Yeah. So if we fix size of each filter, then area of each filter is equal to L into B. Then total number of filters we need to provide is equal to total surface area by area of each filter. So this will give number of filters required. Okay, that's how we can work out. This is one method. Second method, this is. So one or two filters extra we provide standby if mentioned. Otherwise we ignore. That's all. This is a slow sand filter. In case of rapid sand filter, so many number of things we are expected to find out. In addition to this, many things are expected. Rapid sand, in case of rapid sand filter, first as usual we work out. So rapid sand filters are also designed for rate of filtration. First we will work out total surface area of rapid sand filter required. This is Q by rate of filtration. Normally rate of filtration for rapid sand filter is very high. 3000, he will give you these values. You need not worry. Liters per hour per meter square. Okay? Then as usual, method 1, fix number of filters n. Find size of each filter. Second method is fix size of each filter, L and B, find number of filters required. After this, in addition to this, you are expected to find out percentage filtered water required to backwash. Filtered water required to backwash filter. This is also expected. Okay. So percentage filtered water used in backwash is equal to, or required to be used in backwash is equal to, it is rate of backwash into duration of backwash by rate of filtration into duration of filtration into 100. So you can work it out by using these parameters. Okay. Generally, usually you get anywhere between 2% to 6%. This is the one. Next, what else is expected? Head loss during filtration. Head loss during filtration we work out by using equation FZV square by ZD into 1 minus N by N cube. FZV square by GD into 1 minus N by N cube. This is head loss during filtration in case of rapid sand filter. Then head loss during backwash also are expected. Head loss during backwash of the filter. So head loss during backwash we work out by Z into 1 minus N into S minus 1 is also equal to ZE into 1 minus NE into S minus 1. And we can also brought out relation between ZE by Z is equal to 1 minus N by 1 minus NE. ZE is nothing but porosity of expanded bed. NE is equal to, ZE is thickness of expanded bed. NE is equal to porosity of expanded bed. Okay? We solved numericals also based on these equations already. This is called Karman and Kozny equation, that head loss during filtration. This is also very useful equation. And in addition to that, rate of backwash also you are expected to find out. So rate of backwash or velocity of backwash water is equal to the settling velocity of the sand particle in filter media to the power 4.5. Velocity of expanded bed to the power 4.5. And the settling velocity you can use same equation, Stokes equation, G into S minus 1 d square by 18 nu if laminar flow condition prevail. Otherwise any flow condition is a respective equation you have to use. So velocity of backwash water or rate of backwash you can work out by using this equation. Then backwash water flow rate is equal to velocity of backwash water into area of filter. Length into B will give discharge through backwash water. Backwash water discharge through filter media. That also are expected sometimes. So this many number of things we can work out related to filter. Okay. In addition to this, anything extra? We can also work out lambda. We can brought out relation between concentration of particles removed and efficiency. 1 by Z into 100 by 100 minus efficiency. This formula also we used where lambda is a filter constant. For a given filter it always remain constant. So this equation also we saw. We solve few numericals also based on this equation. Understood? Hamsaraz Saroj, echo is coming, voice is not clear. So what can I do? Hamsaraz, echo is there, huh? Why echo problem? Okay, I'll correct it in second session, okay? Echo is there, Ankit Kumar? My voice is not clear. My voice is not clear, Ankit. Clear, okay? Okay, some people it is okay, some people not okay, means something wrong with your system. Your connection you have to verify, sir. That is about filtration, including filter kinetics also we wrote there. Then coming to disinfection. These four topics only important: sedimentation, coagulation, filtration, disinfection into water treatment. Coming to disinfection, the first numerical you can expect from disinfection is right. What is expected first numerical? Percentage HOCl present in water is equal to 1 by 1 plus K by H plus into 100. Okay? And HOCl is known, OCl you can find out. So HOCl and pH relation. For a given percent HOCl, you are expected to find out pH. For a given pH, you are expected to find out percentage HOCl. This is first kind of numericals. So this you can work out by using this expression. By ionization equation, we wrote this. You can brought out relation between HOCl and OCl. HOCl is powerful than OCl, therefore we need to maintain HOCl. That's why percent HOCl we calculate. Then HOCl concentration in water is equal to, after adding chlorine to water, HOCl concentration is equal to, it is chlorine dose added to water into percentage HOCl. So you can work out HOCl concentration. As long as you maintain HOCl concentration constant, disinfection also remain constant, doesn't change. Okay? That is first kind of question. Second kind of question is chlorine demand. So chlorine demand of water is equal to, it is chlorine dose added to water minus residual chlorine present in water. Cl2 demand. Chlorine, you can write Cl2, no? chlorine demand of water is equal to chlorine dose added to water minus residual chlorine.
Sometimes chlorine dose
also they will ask. Chlorine dose is equal to chlorine demand plus residual chlorine. If you add, then you will get chlorine dose. So based on this equation, they keep on asking questions in GATE exam. Okay. In addition to that, it is linked to bleaching powder dose. Bleaching powder dose required is equal to bleaching powder dose. Right, shortcut BP dose required is equal to, it is chlorine dose required by available chlorine in bleaching powder. Okay, from this you can work out what amount of bleaching powder required. So based on this, they keep on asking questions. Total chlorine, total bleaching powder required per month, per year. So total bleaching powder required per day is equal to Q into bleaching powder dose. So substitute Q in mld, bleaching powder dose in milligram per liter, you get this in kilogram per day. So based on this also they are asking questions. Per month how much required, per year how much required, per day you know, per month, per year you can work out. In addition to that, percentage removal of organisms. Percentage removal of organisms from water is equal to, called efficiency, it is N0 minus NT by N0 into 100. N0 is initial number of organisms, NT is equal to organisms remain in water at any time T. Or sometimes he is also asking log removal. So log removal is equal to, it is log 10 N0 minus log 10 NT. So couple of times in GATE exam, based on this, they have asked these questions. You can also find out NT, number of organisms remain in water at any time T is equal to, is N0 into e power minus kT. This equation is known as Chick's law for disinfection. So if you substitute that, efficiency can also work out, right? Substituting this NT value here, then it is 1 minus e power minus kT into 100. Using this expression also you can find out efficiency of removal. Okay. Based on this, left and right is asking questions in GATE exam. In addition to that, the relation between chlorine dose C and contact time T. So relation between chlorine dose C and contact time T is given by an equation. C into N to the power T is equal to constant, where N is a dilution factor. So time available is more, then less dose also sufficient. So chlorine dose required straight away inversely proportional to time. Time available is more, small dose also sufficient. Time available is less, more dose is required. So this time you can also work out. Time is nothing but contact time, this is, and it is something similar to detention time. Then used based on this you can also find out volume of disinfection unit. Volume of disinfection unit required is equal to Q into contact time or detention time. So based on this also they are asking questions in exam. Okay, these are the possible questions from disinfection. In addition to that, breakpoint chlorination. Using breakpoint chlorination, questions are asking in GATE exam. So breakpoint chlorination is a test conducted taking chlorine residuals on y-axis and chlorine dose on x-axis. We conduct test then you can find out break point. The point from which a curve rises 45 degrees is called break point. So this point is called break point. From here 45 degrees it rises. So dose against break point is called this break point. Dose against break point is called chlorine dose at break point. Chlorine dose at break point. Small pp I'll put break point. Capital PP means you'll understand bleaching powder. Chlorine dose at break point. Then chlorine residual at break point is called, this is called combined chlorine residual. Chlorine residual in the form of chloramines. Combined chlorine residual. And above 45 degrees, whatever chlorine residual is there, that is free chlorine residual. Free chlorine residual. So total chlorine residual is equal to free chlorine residual plus combined chlorine residual is nothing but total chlorine residual. So both combined chlorine and free chlorine both will give protection in water. So that's what we are expected to find out. So total chlorine residual is equal to, it is combined chlorine residual plus free chlorine residual. Okay. Then what is combined chlorine residual? Combined chlorine residual is equal to, it is chlorine residual at break point. I wrote it as BP. And free chlorine residual is equal to actual chlorine dose added minus chlorine dose at break point. That will give free chlorine residual. Because 45 degrees it rises means what? Beyond this 45 degrees rise means x is what? 45 degrees x is equal to y. So whatever is there beyond 45 degrees x axis, same will be there on y axis. Therefore free chlorine is equal to actual chlorine dose added minus chlorine dose at break point. That's how we can find out using this break point chlorination test. So these are the things which you need to remember in case of chlorination, disinfection. Chlorination only important in disinfection. Okay. Now I'll stop here. We'll have lunch break. Again I'll start at 4 o'clock second session. So I'll continue from there. I'll try to finish up today. This is micro revision. Only formula I am writing. Okay. This may be very useful to the student community. After attending that revision class, after solving those numericals, once again you go through this, you can recollect everything. Okay. So I'll stop now. Again we'll meet at 4 o'clock. 4 to 6 I'll finish up. I'll finish up total up to air pollution today in every respect. Okay. Again we'll meet at 4